So we're happy to have with us today Daniel Barzilai from Weizmann Institute, student of Raj Shamir, who constantly sends us interesting students with interesting talks. So we have a lot to hope for. So thank you.
Okay, thank you. Thank you for having me. So indeed, I'm going to talk about two different papers that I worked with Raj Shamir. They're going to be completely unrelated. So in the first one, we're going to talk about theory of AI slop, if you want to call it that. And in the second one, we're going to talk about, why sometimes gradient-based methods can fail when there's actually other methods that work well. And so the first one's like on Europe's paper, and the second one's going to be in court in a month or so. So we'll start with the AI slop. So by slop, I just mean, synthetically generated data that's not that good sometimes. And, like the early generative models that we all know, I mean, they mostly trained on real data that humans created. But as you can imagine, everybody uses them. They fill the internet. Sometimes it's good, sometimes it's bad, but whatever it is, over time, data sets get a lot of synthetically generated data within them. So, the next version of the models trains on data sets that have some AI-generated data, and then they will be used to train another model, and then that model will also generate data. And this loop can go on as many times as you want. And this raised a lot of concerns. Like already we see a lot of fake data in common data sets. And like what happens when we push this loop to the extreme? And people called this model collapse a few years ago because there was this very big concern that if you do this loop a lot of times, like the model performance is just going to completely drop. It's going to collapse. And so like the early papers that looked at this were mostly experimental. And they created these sort of experiments that, others argued with them later somewhat. But generally, like you start with some generative model that's trained in the regular way that you all know, and it looks good. And then you train more models using the outputs of the previous ones. And when you repeat this multiple times, eventually you reach models that produce images that don't look so good. And there's also similar phenomena with other modalities like text. But there's really like no consensus regarding how serious of an issue this is. There was another paper just a little bit later than the previous one that showed, like in the previous paper, they completely threw out all the real data and trained only on the data that the previous model generated. So then a different paper says, well, what if you mix between real data and fake data and suddenly model collapse doesn't look that bad? Right? So there was like a lot of discussion and a lot of debates, and it's really hard to kind of track this phenomenon experimentally because it's very delicate. And so maybe just to set some notation before I keep talking. So the general framework we're going to be in is what I call an iterative maximum likelihood estimation. So we're just going to start with a family of distributions, p theta, and theta are just some parameters that we're trying to learn, like the parameters of a neural network. And there's going to be some ground truth theta star. And we start with a data set that was generated from theta star. And then at each iteration, we fit a model to this data set, and then we generate a new data set from that model. And the way we fit a model is just by minimizing the cross-entropy loss, just like everybody does in practice, or equivalently maximizing the log likelihood. So this is called the maximum likelihood estimation, or MLE for short. Any questions about the setup? Perfect. Okay, so as I said, like there's a lot of different settings you can talk about when you're talking about model collapse, and they matter. So the first papers talked about a setting where you're replacing the data at each iteration. So every time you have some data, you train a model, you generate some data, and you don't use the previous data at all. You can also talk about a setting where data accumulates slowly, where in each iteration, you combine your previous data set with this new synthetic data. And the difference is very big. So with replacement, like even very, very, very nice like synthetic distributions can already suffer from model collapse very quickly. This is like what the first papers on the topic showed. So there's this paper by like Ilya Shumailov et al. And like even for Gaussians, if you're replacing data at each iteration, eventually it's going to collapse when you do maximum likelihood estimation. And it's actually not that difficult to show because it's well known that if you do maximum likelihood estimation for a Gaussian and you estimate the variance is actually going to be a little bit biased. So in expectation, when you estimate the variance with synthetic data, you're not actually going to get what you should. You're going to get what you should up to some 1 divided by n factor. And when you repeat this many, many times, these errors really accumulate. And in the limit, when you repeat this loop, infinitely often, you can get model collapse. Now, of course, you can argue, okay, t has to be very big here to get model collapse. And again, this is a very synthetic setting. But I think it's like the first way that people actually show this phenomenon exists. And we actually see that in probably more realistic settings, it's not that big of an issue as it is here. Other questions? Okay, so we are going to look at the accumulating setting because, okay, it's arguably more realistic. It's a bit harder to analyze theoretically, but if the motivation is like, data sets that naturally grow and the internet that slowly accumulates synthetic data, then you do want to talk about data accumulation rather than replacement. And the main theorems that we show is that if the family of distributions that you're working with is sufficiently nice, and I'll say in a minute what I mean by sufficiently nice, then you're not going to get model collapse even when the number of iterations is huge, like more or less exponential in the number of samples at each iteration. But without these sort of assumptions, you can create very, very, let's say, synthetic examples where you do get model collapse and you can make it happen arbitrarily quickly. And there's also like a very big gap between these examples because, okay, like the positive examples are like for very classical, nice assumptions. The negative examples are when you have almost no assumptions. And in between, it's still kind of a gray area.
Just to make sure about your previous slide.
Yeah.
Do you claim there's a real gap between the replacement or continuous, or just say you're focusing on this because it's more?
No, there is a real gap.
And intuitively, why, if as t grows, the portion of the real examples is becoming negligible? So why should the drift will be, let's say, half as quick, or I don't know, so like, but why should it?
It has to do with how the variance between each model and the previous one is changing, and I'll talk about this more in a few slides. Yeah. Okay, so for the assumptions, first of all, there are cases in general where MLE fails miserably. Like in the middle of the 20th century, people in statistics were really obsessed with coming with very strange examples where this happens. And generally, it's a very well-studied thing, and there's very classical assumptions that under them you can show that, okay, if you just do the natural thing, minimize the cross-entropy loss, it works. With enough data, it works. And so we do want to, of course, be in these settings. We want to talk about settings where, okay, training a model with a cross-entropy loss makes sense. And the assumptions that we're going to assume are really the classical ones that allow for this. Again, there's a lot of literature on this, so you can kind of argue, and there's many different variations. But generally, the main thing that we need that's maybe non-trivial is smoothness. So we're going to assume that when you look at log of your model, that it's sufficiently differentiable. And we also need what we call constant support. So if we don't want there to be some examples where some models say there is 0% chance of getting them and others can get them. So all models have some chance of outputting everything. And I think those are the two non-trivial assumptions. But again, they're still very classical.
making sure when you say sufficiently differential, you mean
I need like three.
Many times.
Yeah, sufficiently many times. I need like 3 derivatives. Yeah. Any more questions? Okay. Okay, so under these assumptions, well, so this is kind of a paraphrased, but what we can show is that for any number of iterations and any samples, any confidence, as long as the number of iterations is not too big, and again, like even if it's polynomially large in the number of samples per iteration, that's still okay. Then the difference between the model at time t versus like the ideal one in KL is roughly going to be on the order of 1 divided by n. And this is actually the same guarantee more or less that you would get for doing maximum likelihood estimation just once. So the error you get after t times when t is very large is really just a constant times what you would get if you did maximum likelihood estimation once. So you're really not paying for this iterative training by more than a constant. So, okay, what's the proof idea? So it was kind of actually a fun proof to work on because I got to read like very old papers, which I never do, and kind of the proof is very similar to some of those. The idea is it's kind of like a classical one. You sort of look at the gradient of the loss, and you Taylor expand it, and you say, okay, how does it behave around this area? And the main thing that's kind of interesting is that when you look at the gap between each model and the previous one, then it's roughly going to be on the order of 1 divided by nt squared, and not 1 divided by nt. That's like where the magic happens. Because then when you sum up over as many t's as you want, like 1 over t squared, it just sums up to like pi squared over 6. And so it's finite, and then at most you're never going to be beyond 1 divided by n, more or less. Actually, there's another paper that had this very mysterious title on this topic, like the universality of pi squared over 6, where they did like a similar analysis to this. And it turns out, and actually they never wrote it in the paper, like this was just the trick. Like you sum up, you get pi squared over 6, and this was the title of their paper. Also, studying model collapse, but slightly differently. And then, okay, what about the assumptions and the negative results? So, as I said, smoothness is probably the most arguable assumption, at least for neural networks. And so, okay, are there weaker assumptions? Can you drop the ones from the positive result? Like, do you need any assumptions? Like, if you just set up a scenario where a maximum likelihood estimation is consistent, like, is that enough? And experimentally, it was extremely difficult to find an example where you do this repeated training and you accumulate data and it breaks. Like, it was very, very difficult. Almost always it looked like this, where like on the x-axis, I have the number of times I repeat the iteration, on the y-axis, the error. So like, okay, the first time you get some non-negligible error and it grows a little bit, but very quickly it plateaus and that's it. And almost any distribution I tried, this is what the graphs look like. So for the negative results, we did eventually come up with something, but I will say these are very synthetic examples. And that's why I'm also saying there's a kind of a gap between the positive results that probably assumed a little bit more than they needed and the negative results, which like they're the worst distributions you could possibly come up with. But it was really necessary. So in the paper, they come in 2 flavors. And I won't go too much into the subtleties, but essentially you can make model collapse happen arbitrarily quickly. So in these examples, I'm taking a family of distributions which is nice enough that training on the cross-entropy loss works. So maximum likelihood estimation is optical consistent. But if you repeat the loop 2-3 times, it already breaks arbitrarily badly. And what do these distributions look like? So you can think of there being sort of some main area where like this is the important part. And then there's something unrelated, which is like a very ugly peak. And so like the original distribution, you can think of there being no peak at all. And when you try to estimate it, there's going to be some error. And when there's a small error, then you get a different distribution, which sort of looks like the original one, plus something unrelated completely. And you need that something unrelated to be significant enough that it makes training the second time break. So it's a very synthetic example, but it does show, this is an important part, that the assumptions, at least some of the assumptions from the positive theorems are actually necessary. Are there questions? Okay. Okay, so let me summarize until here. So there's really a lot of papers nowadays on model collapse, and I think there's like a lot of interesting follow-ups that you can do. In our paper, like, okay, under some assumptions you don't get model collapse, under some assumptions you do, but we can talk about like, okay, how can you close this gap? And you can really complicate the setting and make it more interesting and more relatable to what actually happens in practice. Like, what if there are multiple models involved? In our paper, we talked about, okay, you can minimize the loss exactly. What happens if, you take into consideration optimization issues, approximation issues? How does that impact model collapse? You can talk about how you actually help prevent these issues in practice, because, okay, here, this is a theoretical paper. For us, a constant is not important. In real life, a constant is very important. So there's still a lot of work to be done. Okay, I'm going to move on to the other paper. So before I do, anything on this one? Yeah.
Do you have any educated guesses about what assumptions are necessary? Or you focus on smoothness for now?
Yeah. The proofs would definitely need to change completely without the smoothness. I assume that the smoothness should not be too important, though. I think, yeah.
Best derivatives. The continuity probably would be, otherwise everything would
Yeah, you need something like that.
maybe less derivatives.
Yeah, and like in the negative example also, you can't see this here, but like these peaks need to be very, very, very big to offset what's happening here. So also, like, just reasonably well-behaved models in the sense that they don't look almost like deltas should be enough. Okay, so now we're going to talk about SGD and when it can fail and why. So, like we've all gotten used to running SGD with neural networks on just about anything, and on just about anything it seems to work magically. And so you might actually like wonder, okay, are there problems which you can solve efficiently but SGD fails? Like, of course, there are problems that are very difficult for any method, right? Like NP-complete problems, cryptographically hard problems. But these are less interesting from our perspective because like it's not specific to machine learning. Everything's going to fail on them. But are there problems which are actually easy in general, but SGD fails on them miserably? And the classical example that people will give for a problem like this is what's known as the parity problem. So you can imagine getting inputs that are just uniform on the cube, so minus 1, 1, d. And there is some subset of indices which is unknown. And the target function that you're trying to learn is going to be a product of these indices. And in general, here there is no noise for the target function. And in this setting, it's like exactly solvable because you can write this like as a linear system over F2. Gaussian elimination works fine. But like if you try running any gradient-based method, basically with like any model, do all the tricks you want, like it's not going to work. So, just some old graphs, like even when the dimension gets to like 30, the accuracy just roughly stays the same. You don't even have to get to that high of dimensions for this to become very, very difficult. And okay, I think it's important to try to understand why such things occur. So when we look at SGD, a lot of times the natural way to think of SGD is to sort of split it between what happens in expectation versus the gap between the fact that we're using, a finite amount of data in each iteration versus this expected value. So when we take the expectation over the entire data set, we call this the population gradient, the population loss. And the gap between, the gradient that we get from one sample versus what we get in expectation, we can just think of this as some noise, the SGD noise. And the annoying thing about analyzing SGD is that this noise is like, it's terrible. It doesn't satisfy any assumption that you would want anything to satisfy. Like, it depends on the data, it changes throughout time, it's not isotropic, like coordinates are not independent. Like any assumption that any probability book has, this doesn't satisfy basically.
It's unbiased.
It's unbiased. Okay. It's unbiased. It's a martingale, yes. Okay, it satisfies one. So essentially all lower bounds are really based on creating settings where you sort of toss out this noise and you replace it with something else that you can actually analyze. So one of the main frameworks, for example, is like the statistical query framework. And in this framework, basically, okay, it's more general, but at least when you apply it to SGD, it boils down to just assuming that this noise is adversarial. And SQ comes in many, many flavors. You can also assume that it's like Gaussian or something else very nice, but you sort of have to replace this noise with like a very, very simple thing that you can actually work with. And when you do this, then you can get meaningful lower bounds. For example, in the parity example that I gave, once you replace the noise with like a Gaussian or something adversarial, then you can show that you need exponentially many iterations to converge. The rough idea is that all of these functions are orthogonal to each other. And so when you look at a gradient, it can't point you towards many of them at the same time. And so eventually the noise is going to be like much bigger and you can't really learn anything this way. So in general, SQ is a very good framework because it lets us get rough estimates of how hard some problems are without having to do too much work. The problem is that they don't always hold. And there's already like a lot of examples in the literature of problems where the SQ bound completely breaks. So these do require like very, very artificial constructions. So like with SGD, people were able to construct a very, very synthetic network that basically what it does is it's like it memorizes the samples that it got, and then it runs an arbitrary algorithm. And then when you allow for such things, then yes, SQ can break. And so now the question is, okay, in realistic settings, can we actually get like real rigorous lower bounds and understand why SGD fails for relatively standard scenarios? Yes, I should have said this after I switched to this slide. So can we understand why vanilla SGD, like on natural predictors, fails to solve any classical learning problems? Okay, so the setting we're going to be in is the following. We're going to have some input distribution, and for now it doesn't really matter too much what it is, but I will just say in general, always think of like very high dimensional things. And the target function is going to depend on some lower dimensional subspace of these d-dimensional inputs. So we have some matrix U, and we're going to take UX, and then we're going to apply a simple function to this. And these are called multi-index models, and the idea is that if you actually knew U ahead of time, then this problem would be very easy. So in the parity example, U is basically like the directions of the parity. But if you don't know u, then finding u is very difficult, and until you find u, the gradient is going to be uninformative, the loss is going to be bad, etc. So the predictor we're going to have is going to be similar. We're going to have some w times x, like just a linear layer, and after the linear layer, you can take whatever you want. So this can be a deep network, it can be a transformer. I don't care, I just want the first layer to be linear. And I'm always going to be thinking of a setting where the width is much smaller than the dimension. So in general, like the dimension here is going to be bigger than all the other parameters. And like before, okay, we're going to relate between the sample-wise loss and the population. And we're just going to train everything like via standard SGD, a single example like batch size 1, the most simple thing you can do. And you can, of course, generalize this, but the more you generalize, the uglier the notation becomes, and it's kind of a pain. So, any questions on the setting? Okay. So what's the key idea? Like, how do we actually get meaningful lower bounds in these settings? So let's just assume for the sake of this proof sketch, X is a standard Gaussian. And we're going to just think of the case where we have a single neuron, and the function we're trying to learn is also just like a single neuron. So we have some function phi. We're trying to learn something that is phi of u transpose x, where u is some unknown vector, with phi of w transpose x, where w is the parameters that we train. It's the simplest setting that is tractable. So what does SGD look like? So when we write the when we expand the SGD iterations, the gap between the parameters at time t from time 0 is going to be the learning rate times AT/xt, where AT is just the downstream gradient until xt, and then you get an xt out of it. Right? This is just the chain rule. Yeah, this okay? Okay. So as I said, for the gradient to actually be large and meaningful and for the loss to be decent, you really need W to be close to u in these settings. Like you can actually get very nice bounds on the population loss and the population gradient that depend on how well W is aligned with u. So you kind of need to imagine this picture in not 2 dimensions. But if this is the u direction, right, we want the weights W to be relatively aligned with u. So this is like this purple cone. But when we initialize W in general, it's not going to be. Like if you take a random W, the alignment with u is going to be roughly on the order of 1 divided by the square root of d, more or less. It's going to be small. And so until you find this cone, you're kind of just wandering around. This is like the idea of the proof. So if these ATs were just constants, they're not, of course, but let's just say for simplicity they were, then this sum right here is just like a random walk, and it's not going to help you align with u at all. So you're going to need a very, very long time to align. Now AT, of course, they're not constants, they depend on everything, it's kind of tricky, but what we show is that if they're reasonably well behaved, then they're not going to help you align with the important directions that you need too much. So this is like the main idea. And I should say, what does it mean for them to be relatively well behaved? So for the most part, we just need that, like the maximal values that you can take won't be too far from like their standard deviation. We need their typical size to be relatively similar, or at least on the same order as their maximal size, up to constants that don't depend on the dimension. And this does actually happen in a lot of cases, and we'll see like more specific theorems that you get out of this.
There's the problem of finding the subspace, the interesting subspace, and then there's the problem of finding this function. Of course, had a method to find the subspace, that would make this problem easy. But
here it's trivial because here you already know the function. You just don't know the subspace.
So my question is like, are these results effectively saying this is hard because finding the subspace is hard, or is it even harder than finding the subspace?
No, the entire difficulty is in finding the subspace. once you start getting close to the subspace, it's easy.
Okay, so maybe my question is, do you have a setting where if I would just try to find the subspace, it would have been an easier problem than now that I'm trying to find it in this like sort of roundabout way through this function? And does the fact that I'm trying to get to the subspace through the function make it hard for me?
So yeah, it's kind of tricky. I mean, the thing is that we're not using a lot of the geometry of the function. We're not using a lot of facts about it. So when we do SGD, it's relatively simple. Like we're relatively just pushed in the direction of the gradient. And here the gradient, it's going to be small when you don't have a lot of alignment. The more sophisticated methods, like for very, very specific problems that can do this faster, they really have to exploit the specific structure of like phi, and there's no general purpose algorithm that can find subspaces like this for anything. Like if you think of something like parities, okay, now you can do Gaussian elimination, but in general, there's no magic. Any more questions? So if we go back to sort of like our original decomposition, okay, so we said we want to look at SGD through the population gradient and the noise, then what did we actually show? So let's say if the population gradient is typically very, very small, and the noise is reasonably well behaved in the manner that I just told you, then you really, really can't align the parameters with the important directions that you need them to be aligned with in parameter space. And effectively, SGD is going to be almost as ineffective as a random walk, where the almost just depends on how big the population gradient is. If the population gradient was 0, it would be as ineffective as a random walk. So what does this actually look like for specific problems? So maybe I should just say analyzing the population gradient is actually not that easy in general. A lot of the specific theorems that we give, when the inputs are Gaussian, because when they're Gaussian, you can actually analyze these expected values quite well. And so one thing that we can look at is what we call periodic functions. And so we should think of something like a sine of u transpose x, but the norm of u can be very, very, very large. So when the norm of u is large, like this, oscillates very quickly. And this is probably the most natural way to extend parities to a continuous domain. So because we're looking at Gaussian inputs, this is like the most natural way to talk about something that's like parities. And actually, this problem has a lot of the same hardness issues that parities have. If you receive noisy labels, then just like in parities, it's like cryptographically hard. If there's no noise, then there are algorithms that can solve this efficiently, but they're very convoluted. They're like continuous analogs of Gaussian elimination, and it's kind of a mess. But like no practical method can solve these, and the SQ dimension is very large, etc. So we have a lot of evidence that these are hard, but we actually give the first rigorous lower bound for SGD in these cases. So just for simplicity, we can take the norm to be the square root of D. And as long as the learning rate is not too big, the dimension is relatively big, then the population loss is essentially going to be exponentially small in the dimension, unless the number of iterations you took. This is a very unfortunate typo. Here it needs to be x of d to the third. So this should be an x. It's a bad place for a typo. But essentially, unless the width of, let's say, your network is huge or something like this, you're going to need an exponential number of steps to converge. Questions on this?
Random walk, why does it say that it's close to initialization? Like having a result that says that the chance of finding the right one I can understand.
Mhm.
Why should it be close to initialization and not just drift around?
What do you mean close to initialization?
You say the result is that with high probability the population loss remains close.
Oh, it's just the loss itself is trivial.
Loss is close.
Yeah, the loss. The parameters can drift as much as you want. Yeah,
Sure.
yeah. Okay, and we have another class of like explicit results. So these are via what's called the information exponent. So the information exponent, it's kind of like an annoying technical thing, but it's very powerful, and there's a lot of papers that talk about this since like 2021. If I simplify it a little bit, basically what the idea is, you want to ask, okay, for a given target function f star, how much information does it have in like low degree polynomials? So the information exponent is the minimal k, such that there is some polynomial of degree k that doesn't have a constant term, where this expectation, like the correlation, is not zero. And you can show that this is very related to how hard it is for SGD, because if this k star is very large, the gradients are not going to be very helpful. So that's kind of like the technical thing, and I'm not going to talk too much about how we derive these bounds on the gradients. But if you're willing to believe that, then now you can show that the number of iterations you need with SGD roughly grows like d to the k star minus 1. Again, under very simple assumptions and basically very similar things to before. We just need the dimension to be large relative to everything else, the learning rate not to be too big. Okay? Okay, so we can actually get meaningful like lower bounds for SGD. But there's still like a lot of open questions, right? So like the concrete theorems that we were able to show at the end, they don't exactly hold for parities, because with parities, like the structure of the expected loss and its gradient, it's actually like very tricky. It's combinatorial, so can you actually show rigorous lower bounds for things like parities? Like there's width considerations. In our paper, we just assume that the width is relatively small, when compared to the dimension. What if it's not? Are there other frameworks that you can use? What about other optimizers like Adam, things like this? So there's still like a lot of places that can take this. So this is it. Are there any questions? Okay, thank you.